Good day, I'm Vincent Saxtetter, and this is the After the Age of Fire channel. This is episode 49, recorded on June 13th, 2026. The title Is Human Intellect Accelerating Towards a Transformation? So, are we about to go through some huge revolution in how we think and perceive in our intelligence? A quantum leap, something far beyond what we've done over the last thousands of years. This is a prepping channel for you and for your family line, preparing to flourish and thrive and reproduce during the transition between two eras. We're finishing an era of about 250 years during which we were doubling, the human race was doubling its consumption of just about everything every 22 years, so each generation, averaging across the world's population, had around 2 times more than what the previous generation had. And we're transitioning sometime around now into a new era when we won't be doubling our consumption anymore. In fact, our consumption will be a little bit less, something like our consumption around 1970. So right now we're consuming about 46,000 calories from sources, the renewables, and from coal, oil, and gas. About 41,000 calories of that is from coal, oil, and gas, and another 5,000 calories from renewables, and another 15,000 calories from things that we grow, our forests and our crops. So that comes to about 60,000 calories per person per day, averaging across the whole world. And in the coming era, we'll settle down to somewhere around 30,000 calories per person per day. So a bit less, but nothing like what our consumption was 200 years ago. Far, far, far more than we had on hand 200 years ago or 300 years ago. So in the first episode, the first section of this channel up through episode 38, we were talking about exponential growth, about the doublings that we've been experiencing, and also about how much we'll be able to continue to consume long term from all the various energy sources, and that's how we settled on the 30,000. If you want to go to, if you want to see where those numbers come from and why all the energy sources are so expensive or have so many side effects and consequences that we won't get more than 30,000 calories from any of them, just go back to the episodes before episode 38 and take your pick and work through them. Now we're in the second section of this channel's content, which is about the transition between the two eras, how to recognize it, and where are we in it. So that started in episode 39, already 10 episodes ago. The last episode, episode 48, last week, and this episode were about a certain way that things could go during this transition between the two eras. And we're looking at the possibility that the human race might, in a very tightly coordinated way, reorganize itself to adjust to the new level of consumption that 30,000 instead of 60,000 calories per person per day, and no longer having the doublings. So in other words, that everyone and all groups at all levels, from people to families to clubs to towns to every sort of association towards to governments, in one way or another, tightly interacting either by cooperating or competing or fighting, but through some sort of very intense communication and interaction, may settle on a new way of living that would adjust and live within that 30,000 calorie limit. And this could happen quite quickly, much more quickly than our running out of easy coal, oil, and gas, running out of minerals like the easy coal, easy gas, easy oil, will take decades, generations, but for us, for the human race to execute a reorganization could, at least conceptually or in theory, could proceed over a number of years or even months. So are we coming up to something like that? Another mathematical way of referring to this sort of reorganization, self-reorganization, would be self-limiting growth. That's the phrase that I favor. Or something that other people favor is the singularity. So we're looking at, and so in the last episode we were looking for signs that the human race may be preparing for this singularity, or this sudden reorganization. So the hallmarks of the kind of reorganization that I'm talking about in these two episodes is, first, it's globally organized. It's not the forced behavior that will happen anyway when our doublings end. So in any case, when doublings end in any system, something fundamentally changes. For instance, a fire burns out, or the bacteria in a petri dish exhaust the food in the petri dish, and they all, just by necessity, do something else or die. That's a kind of reorganization. So that's not the kind of reorganization that I'm talking about here. It's something where we do it ourselves, and it's not locally forced on us. So it's in fact, and then you can distinguish between two kinds of tightly coordinated reorganizations. One is the kind that we do ourselves, and another one is where we're doing it, but it's kind of forced on us that we organize for it, but we don't mean to organize for it. So the way that the human body, for instance, as a human body ages, it becomes organized to the point where every part is aging, and every part becomes more and more ready for death, and it's organizing for death. But it's not, the human is not deliberately trying to die. It's just that the body experiences so much stress that the pieces just line up in a way that sooner or later prepares them to suddenly or slowly die. And the same thing with structures under stress. For, say, a bridge that's under stress for 50 years or 500 years, it will gradually develop cracks and so on, and those cracks will get bigger and organize themselves into a structure that sooner or later the whole thing will collapse. It's preparing itself for its collapse long before it actually does so. That's not the kind of organization I've been talking about during this last episode, and this current episode. I'm talking about one we're actually trying to make it happen. We want, in some sense, to make this reorganization happen. And I'm talking about one that's not top-down. That'll be 2 episodes from now. No, it'll be the next episode. It'll be episode 50. It'll be top-down, so where the reorganization is forced by people on top. Instead, what I'm talking about here is a kind of reorganization that's driven by a very strong coordination or competition. Okay, and it could be very quick. I'm not here talking about I'm not a new Marx, I'm not a Karl Marx, and I'm not predicting any particular new world order. It's obvious that after the doublings end, things will be different in one way or another, but I'm not here telling you that the solution to it all is the victory of the proletariat or anything. All I'm talking about is signs that there will, examining whether there are signs that there might be some sudden decision made by the whole human race collectively acting together to reorganize. The signs would be, first of all, an acceleration in tempo in our affairs and the events of the human race. It would be, another sign would be a cycle of booms and busts. um, that 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 points towards something coming up, and a third sign would be a kind of oversteering, where since we're so tightly coordinated, so ready to make a change, that we make a change very abruptly. You see this. We see this with financial markets that go through booms and crashes. That can be a sign of yet a bigger boom or crash coming up. So, in the last episode, we looked at many kinds of indicators, and we found that none of the indicators that we looked at give any sign that we're organizing or getting ready for this kind of reorganization. In particular, you would expect for this type of reorganization that we'd be very tightly coordinated. It might be competitive, it might be oppositions, but we'd all be looking at each other very closely and adjusting and competing or cooperating very tightly. And if anything, today we have much poorer ties, as first of all, the families have dissolved, and now even the nuclear family has dissolved, and the people don't know how to make face-to-face contact much anymore because they're too busy on their cell phones, and just the ties that binds are weaker. We seem to be much poorer at communicating than we were even 30 years ago. Notwithstanding all the digital technologies. And then we looked at, and the relationships of trust and so on are much weaker. Then we looked at indicators in the financial markets and the population. So there are booms and busts in the financial markets, but there's no sign that they're going any faster, any differently than they have for the last 200 years. There's nothing different in the last 30 years. Sure, you can see booms and busts, but nothing that indicates that something's coming up. Same thing with population growth. It's not accelerating, it's decelerating. Our economies are decelerating. The GDP growth is decelerating. Our development of machines and buildings, our techniques for building things, there are tweaks to them, but their cars are basically the same as they were 100 years ago in structure and in the main content, but we're just making incremental changes for all the advertising and all the gloss and so on. There's not that much difference between, say, looking at the exterior of a car, the box-shaped exteriors that we had in 1970, and the curvy, pretty shapes that we have now. It's still a box moving. And so overall, looking at all these indicators and also computerized technologies, if anything, it looks like maybe we're slowing down, but we're certainly not speeding up. So in this episode, I'm going to look at one more type of indicator that something might be coming up. And the idea is that our intellectual development, the human race's intellectual development, might be accelerating, that the human race might be crossing major milestones more quickly every year, and in that just looking at the pace at which things are changing in our consciousness, our understanding of the universe, and our understanding of technology, we might be able to argue that everything is going faster and faster, and therefore extrapolate to something has got to change in a fundamental way, not just revolutions in understanding, but a complete revolution in consciousness sometime in the near future. This sort of thing, this sort of idea is being pushed by people who call themselves transhumanists, and I'll say a word about that in a minute. And it's often called the singularity. Okay, so one way to argue that a singularity is coming up is that is, for instance, you look back to when the Big Bang happened, more than 10 billion years ago. Then you look at when the solar system formed, which is a fraction of that. It's not, you don't, you can, it's most appropriately thought of as a fraction. It's less it's more than the difference, the multiplicative difference is more than a factor of 2. Then you look at when, say, when the first cells were, the first life existed on Earth, okay, and that again is another factor of 2 or more. And then you look at when the first mammals existed compared to when the first cells existed, and that's considerably more than a factor of 2. It's probably more like a factor of 10 later. So you're dividing by 2, by 2, by 10. Then you look at, say, the first humans, and depending on how you count when the first humans showed up, it might be 3 million years ago, or it might be 300,000 years ago. Anyway, it's more than a factor of 10 more recent than when the first mammals existed. Then you think about, say, another milestone might be when we started making stone tools. And then another milestone might be agriculture, which would be 10,000 years ago. Again, 10,000 years ago is at least a factor of 3 smaller than, actually it's a factor of 10 smaller than when the first humans existed, even if you think that we started existing only 300,000 years ago. If you don't count the people, I mean the two-legged beings who walked the face of the earth and did things like us 3 million years ago, if you don't count them as being human, even then you probably count the ones that were 300,000 years ago as humans. So that's at least a factor of 10 smaller. Then you think, anyway, agriculture is at least 10,000 years compared to 300,000 years ago as a factor of 30. Then you think about reading and writing, and this is when the dawn of history, that's when we started writing down history. Before that we have no real history. We just have to look at archaeological evidence. So roughly 6,500 years ago, so that's around a half of when agriculture started. Then you look at, say, democracy, and depending on whether you count Greek or modern liberal democracy, that's smaller. Then you look at the Industrial Revolution. The Industrial Revolution was only 250 years ago. So again, that's much smaller than the other time scales like agriculture, reading and writing. Then you look at the nuclear bomb, only 60 years ago. You look at, say, next genome sequencing 20 years ago. Okay, and you notice that you say that. So anyway, the argument runs like this: you lay out a number of milestones, and you say, well, it's obviously the milestones are going. They're not happening on a metronome. They're not happening roughly every million years, for instance, or roughly every 1,000 years. Instead, the time it takes to the next event divides by 2 or divides by 5 every time to the next, and because the time required divides by some number instead of adding some years, you divide the number of years divides by 2, for instance, or by 5. Whatever number you get from this analysis, which depends on the milestones you've chosen, you argue that things will, if the last milestone came 5 years ago, then the next milestone will come after 2.5 years, and the next milestone after a year, and the next milestone after 6 months, 3 months, and so on. And so you'll have an infinite number of milestones of these huge revolutions within, say, the next 10 years. Okay, that's the way the argument goes. If the time scale is accelerating, in other words, if things are getting faster and faster and faster, if the speed at which revolutions happen multiplies instead of staying roughly the same, if you don't get a revolution every 1,000 years, instead the next revolution is faster than and then the next revolution is even faster, then you can, by extrapolating, say that we're going to meet a revolution of revolutions, a mega revolution, in a finite amount of time. And so many authors have looked at this sort of analysis and done other lines of analysis and claimed that a singularity, a mega revolution, a transformation of consciousness could occur, is likely to occur by 2050, so 25 years from now, or at the latest 2100. But in general, or many of them say before 2050. Often nowadays, this line of reasoning is connected with AI. Maybe they think that they suggest that what's going to happen is that we'll figure out how to make computers conscious, or how to transfer a person's consciousness to a computer, so that in theory that the person could become immortal by living in a computer whose parts are replaced even when his body dies. Or maybe that person's consciousness could be again transferred to something else. Or perhaps you could make people have superhuman powers with robotics or prosthetics, or having augmented intelligence. Or maybe you would have a computer, an AI computer that grasps every piece of knowledge and does super reasoning. Anyway, or overall, the idea is that we go beyond being human, that humans are replaced by something that's beyond human and superior to humanity, and that us meat machines are just the scaffolding for the next step in the evolution of the universe. So that's called transhumanism, and it's talking about an idea of there being a point where this kind of revolution occurs. That time would be called a singularity. So I want to talk about this in this episode. Overall, I'm going to say no, there's no sign that we're on the way to that. None at all. There's a sign that certainly there's continued technological developments, but there's no sign of an acceleration towards anything in particular, or any particular acceleration. And overall, there's really no clear sign of an acceleration in the human race's scientific progress. It seems to me that if anything, we are slowing down. So I'll discuss I'll discuss physics, because I'm a physicist. I'm a theoretical physicist. I know a lot about it. I have a lot of experience with theoretical physics, so I can talk about that firsthand. And I'll also talk about genetics and computing, because those are the two fields of science that have shown the greatest progress over the last few decades. Actually, computing, I already discussed in the previous episode, and I'll discuss it more in the episode 51, 2 episodes from now, which will be about computing and AI. So that'll be the topic, computing and AI. So first I'll discuss physics, then I'll discuss genetics, and already we saw in the previous episode that as far as hardware goes with computing, there's no sign that, in fact, there's plenty of sign that we're slowing down. The computer chips, the speed of computer chips was doubling for several decades, and that all ended, I forget, in 1990 or so. Since 1990, the speed of computer chips has remained the same. The number of transistors that you can pack on a chip is also, we were able to still continue packing more and more on a chip until recently. But but we're reaching the end of that right now. How many transistors you can put on a chip, and so in terms of the hardware, we're pretty much at the limit. But now for physics, I've studied many different types of theoretical physics. Has many branches, and I've studied many of them, and I'm familiar with many of the techniques, and I bet I'm familiar with almost all of the techniques and fields of theoretical physics, and I'm rather good at several of them. So I feel like I can speak with authority here. I can speak with, it's not a feeling, it's the truth. I can. There is progress in theoretical physics and in physics in general. The problem is that when we look at the previous centuries, the progress over previous centuries since Newton was extraordinary. There were huge developments that went on decade after decade, century after century, and it's hard to be at all sure that the developments over the last century are of the same rank as the ones before then. There are important developments, but I don't see any way to say that what we've done over the last century is better or even equal to what happened before then. Certainly lots of good physics and some revolutions, but they look to me like they're not quite as important as the revolutions that happened in previous centuries. So in some of the previous centuries, like, there was the invention of calculus, which enabled people like Newton and Leibniz to track the movement of planets and galaxies and understand why the planets move the way they do around the sun. There was the understanding of light and the development of what's called Maxwell's equations, which govern light, but the whole spectrum of light going beyond visible light, so like microwaves and ultraviolet and thermal energy, every kind of light, X-rays, many kinds of light that are known under names, and then there was the discovery of how heat works, thermodynamics, how heat flows, and that was a key part of the development of engines. In fact, the development of engines was our discovery of how to make engines, and then our desire to make better and better engines and different kinds of engines was a key driver of our study of heat. And we finally figured out how it worked, what heat is, and then we went deeper and understood the details of like heat is actually the vibrations of atoms and of molecules, and it's a statistical thing of many billions of billions of molecules and atoms vibrating and oscillating, jostling against each other. And heat is a description of a collective collective descriptor of all that very complicated behavior. So Boltzmann played a key role in this, and we developed the idea of entropy, and then we developed the idea of forces and momentum. That was back with Isaac Newton. But then as time went on, we also developed the idea of energy, kinetic energy, and then understanding that heat is also a kind of energy, and all the kinds of energy, and understanding that energy is conserved. and we also developed the idea of different phases of material, like fluids, solids, liquids, and plasmas. And we just cleared away, all sorts of previous ideas, in fact, that persisted over the last centuries, even until quite late, about the way the universe worked. And these were all just huge revolutions. It's hard to exaggerate how important they are, and they stand as the foundations of all modern physics thinking and all modern engineering and sciences. Understand these concepts that we've developed over the last hundreds of years, the ones I just listed. So this is a kind of a pantheon of so forces, momentum, motion of planets and galaxies, light, Maxwell's equations, heat, thermodynamics, statistics, and entropy, Boltzmann's law, forces and energy, conservation of energy, and the phase diagram and phase diagrams and analysis of different kinds of phases. And in my opinion, these are absolutely fundamental. You just can't do physics without these. The last major additions to the basic foundations of physics occurred between 1900 and 1927. They were quantum mechanics, special relativity, which has to do with when things go at speeds close to the speed of light, and it also has to do with conversion of mass to energy and energy to mass, which is what happens in nuclear bombs and in the sun. And then a third major development around the same time was general relativity, which is a way of understanding gravity, and in particular black holes. And these were developed over about 30 years, introduced over about 30 years by mostly by European scientists, but also by some American scientists in collaboration with them. So anyway, that ended about 100 years ago, and those are the last major additions to the foundations of physics. Nothing else compares, and those are the only ones that I think are clearly so foundational now that they belong with that other list that I already recited for you. Since then, I think the best candidates for concepts or of fields of knowledge that may join that pantheon of foundational concepts, I think there are two possibilities that may become absolutely foundational for physics. One is, and these came in 1970, between 1970 and 1980 or so. One is the area that I call tuning. I've discussed tuning in previous episodes, and I mean things like chaos, like self-organized criticality. I mean complex systems, the butterfly effect, fractals, things like that. That all came together between 1970 and 1980, and sort of took off around then. And then another key concept that's come up is the concept of scales, that length scales of that something the world, when you look at the world at a particular, say, bigger objects like well, I like the human body as an example. You look at the human body is made out of organs, and those organs are made out of, say, the skin is one organ. You look at the skin, and that's made out of particular functional units, say, sweat glands and sensors. I forget what you call them. There's also blood vessels, and you look at all the things in the skin, and then you find those particular functional units in the skin, and those are made out of cells, and the cells are made out of out of organelles. And you look at each of these, if you look at them through a microscope, and you tune the you change the focus of the microscope from the skin to the functional units within the skin, to the cells, to the organelles, to something smaller than an organelle, to the molecules, and at each of those length scales you'll see a completely different world. So that's the idea of scales, is that when the laws of physics, or the laws that govern a particular world, can be completely different at one scale than at a larger scale, and even different at a larger scale. There can be interesting relations between the different scales, and fractals are an expression of that sort of idea, that you can have, for instance, a tree where every branch has 3 sub-branches, and the sub-branches all have 3 more sub-branches. That's a very simplistic representation of the idea that there could be some relation between the different scales. But this idea that really you have to pay attention to which scale you're at, that a description of a description of what happens at one scale, say a set of physical laws at one scale, may be useless for describing what happens at another scale. That was developed in around 1970 to 1980, maybe starting in the 60s. Those are the 2 best candidates for joining the pantheon, but I don't think these 2 concepts, which I call tuning and scales, another word is the renormalization group for scales, I don't think that these have gained yet the same importance as the other concepts I've listed for you, such as energy and forces and fluids and special relativity and Maxwell's equations. They're on their way perhaps towards that, but they're not yet quite at the same level. So, and already those were both introduced by 1980 or so already 40 some years ago. Other than these things, we've seen largely incremental progress in physics, and many fields of physics, subfields of physics, seem largely static. For instance, nuclear physics, the study of the nucleon within an atom, of the nucleus within an atom, the heavy part in the middle of an atom, has remained largely static since around 1950. Now, there are some important developments that have happened along the way, and that some people may argue count as revolutions, and I'll list some of them, but I think none of these have become absolutely foundational for all of physics yet, the way that the concepts, the pantheon that I've already laid out for you has already. Okay, so one of them is the study of what's called strongly correlated systems. Another one that's closely associated with that is called high temperature superconductivity. Another even more recent one is topological physics, which I've worked on a lot. Another one is ab initio computation of materials properties, also called DFT. There's been some extraordinary developments in astronomy, but they haven't become foundational for all fields of physics yet, though they're just amazing to see the universe with new eyes. And then there's something called the standard model of particles, and along with that there's something particular, a description of what happens inside the neutron and proton called QCD. And then another thing that some people think is revolutionary but doesn't seem to affect anything at all yet is string theory. So I don't think that's even a candidate. But these are candidates that might be on their way sooner or later to become foundational, foundational for all of physics. But so far they're not there yet. So overall what I'm saying is that the foundation of physics today dates to 100 years ago, and most of it to long before then. It was developed over several hundred years, starting with Newton, and those were hundreds of years of just extraordinary revolutions after revolution after revolution, and by now, and the last major revolution ended around 1930 with the introduction of special relativity, general relativity, and quantum mechanics. There have been, and then the last things that could turn out to become fundamental to physics happened around 1970 and 1980. So, and it's not clear that they will gain quite the same stature as the previous developments that ended around 1930. So what I'm saying is, overall, there's no sign that physics is accelerating. If anything, it seems like it's going slower. And along with that, it seems like the overall quality of physics seems to be decreasing, at least to me. The way this has gone is that until World War II, there were not that many physicists worldwide, and many of them were extremely intelligent. And their articles and the physicists themselves often showed flashes of brilliance. Quite a few of the physicists were geniuses, and in general, the level of discussion was extraordinary. And then around World War II, while during World War II, physicists provided for the world, they provided nuclear bombs and they provided radar. And then very close friends and associates in mathematics provided cryptography, which was essential for breaking codes, and was very important for the direction of the war. And immediately after that, the cryptography developed into computers, the first computers. And also the nuclear effort also drove the development of computers. So after that, after these, we had a World War II, and the governments, any governments that were interested in global power, really wanted to feed the goose that had laid the golden egg, and so physicists commanded lots of money from. In fact, I think physics among the sciences has been very privileged, and so we've experienced exponential growth. The number of papers that we publish has grown. It's been doubling every 6.5 years, and the number of physicists has been multiplying worldwide. And by now, there used to not be that many physics articles published worldwide. Now there are, depending on how you count them, it's somewhere between 100,000 and 1 million per year. It's impossible to keep track of them all, even if you work real hard at it. And also physicists are accustomed to being treated more or less like royalty. We often, at least the ones of us, those of us who are more successful, often get to stay in luxury hotels, go on jet voyages to exotic locations, to have workshops and conferences together, to give talks. We're treated to royal banquets, and we're treated with extreme care. And even though I'm not a particularly successful physicist, I've gotten to enjoy a lot of that myself. And under this sort of hothouse treatment environment, the quality is just not nearly as, if you publish 100,000 or 1 million articles per year, you just aren't going to have the same quality. In fact, the quality is poor, and the brilliance that many physics articles used to have is pretty much absent. So I'll talk a little bit more about why it's that way shortly, but overall I'm just saying, there's more of us, but our progress is not as good as it was. and there's not much reason to expect progress to be any faster than it was. Now let's go on to genetics. So we spent episodes 26 through 28 on efforts to genetically improve plants in our harvest from the world's plants. And overall, after doing a detailed discussion, and before that there were a couple episodes discussing background of how plants work and what, so you could prepare to understand what kind of genetic improvements you might want to make to a plant to get a better harvest from it. But anyway, overall, the final verdict, which I think was in episode 27, was that we can expect over the next 30 years very little improvement in our total harvest from the world's plants, at least if we're thinking about the improvement that's due to genetic improvements. Okay, we can expect that our genetic work can at most give us tens of percent in harvest, tens of percent increases, maybe 10 or 20% increase in our total harvest worldwide, if we're lucky and if we work real hard. Okay, and it may not even do that over the next 30 years, and we can be quite sure that if we continue to pursue this for then the maximum possible harvest over the next centuries, 1 or 2 centuries, and the total harvest that we could get from our plants is a factor of 2. So there's this is discouraging because we have now genetic technology that was unimaginable. I think it was after World War II that people discovered DNA and how it's laid out, and now we're able to sequence DNA, so we can look at an organism and we can find every single bit of information that's encoded in its DNA. Analyze that, so we have a far better, and we're able to manipulate it. That's something in the last decade or two, that the kind of manipulation and changes to DNA that we're able to do now, we have amazing control over DNA and are able to alter organisms, just unimaginable power. So that the idea that with all this new knowledge of the DNA information within various organisms and all the new possibilities for manipulating it, that could give us only tens of percent over the next 30 years and only a factor of 2 over the next centuries, is rather discouraging. And then alongside that, there's something wrong in the system, in the overall atmosphere of the genetics community. And I'm not meaning to target only the genetics community. I think it's true in physics too, and in every other science. I'll get into this in a minute. But just as an example, I already brought this up during, I think, episodes 26 or 27. There have been hundreds of papers that have claimed that they made a genetic improvement to a plant and that it therefore became more drought resistant. But those papers did not sort out whether they had made a drought resistant plant or whether they had just simply made a stunted variety of the plant. In other words, a plant that grows slowly and develops small leaves and doesn't get very far. Because a plant that grows slowly and therefore won't use as much water, and therefore will seem more drought resistant because it's using less water. It needs less water. Never mind that it will never give you a crop. Okay, and hundreds of papers have claimed drought resistance without proving that their new genetically altered plant was able to give a crop that was equal or even comparable to the or that it would give any crop at all. So something is wrong when you can publish hundreds of papers claiming drought resistance without proving a thing. Another problem with genetics is that even when you can pinpoint and treat a disease's exact origin, there's an effort to pinpoint when you can pinpoint the exact genetic origin of a disease, to then try to treat it. And even when you can pinpoint it, in general you get nowhere. So a first example is Down syndrome. Down syndrome is caused when chromosome 21, which should have 2 copies, one from the father and one from the mother, instead has 3 copies. It's not treatable. What we have managed to do, which is not an improvement, absolutely not an improvement, is to be able to test the child inside the womb and then kill the child if the test shows that the child has Down syndrome. It's not treatment; it's just murder. Okay. A second thing a second kind of disease that we know exactly where it originates is something called Angelman syndrome. Now you may not have heard this, and this one should in theory be much easier to treat than Down syndrome, because it's not a whole chromosome that's wrong. It's one particular element of the chromosome, of one chromosome, that controls the production of exactly one protein. And so it's as conceptually easy and simple to understand as a broken leg. It's just exactly one thing is wrong, and that exactly one thing that's wrong is that if you have this particular mutation, the Angelman mutation, then your body does not produce a certain protein called UEB3A. Okay, UEB3A. What does it do? Your brain works by one neuron triggering another neuron and sending messages that way. One neuron sending a message to the next, and that message is sent by releasing some chemicals into the gap between the 2 neurons. And of course, those chemicals, after they're released, after the message is sent, need to be cleaned up. And UEB3A is crucial to cleaning up those chemicals that send the message. So overall, it's as if your neurons were always sending messages to each other, as if you were very excited. Okay, it's a stimulant. It's as if you're permanently overdosed on stimulants. And one of the common side effects is seizures. But overall, the consequences are pretty comprehensive on the human body. Somebody with Angelman syndrome, with this one particular deletion, where this gene for producing UEB3A is deleted, will generally in fact, they just are unable to develop language. They may learn to recognize a few words. They generally can't say any words, but in general, it's hard to tell whether they recognize any words at all. And certainly, the concept of sentences and grammar or anything, or, being able to speak, just is not there. They generally have grave difficulty doing any basic activity, feeding themselves, using the bathroom, controlling their use of the bathroom, walking, and generally need 24/7 care for their whole lives. Have problems with the constipated. So just even the most basic things that you wouldn't necessarily see in a relationship, say between the function of their stomach and intestines to their brain, but in fact your brain is very, very involved with every aspect of your body's activities. It's really a crippling. Now, one thing, fortunately, is that these people are able to recognize other people, are able to love other people, and really enjoy, and are generally far happier than most people. They're incredibly happy, and they love to laugh. Okay, So what about therapy? We know that there's exactly one problem. It's an absence of the UEB3A protein. And it turns out that even though we know exactly what the problem is, there's not much we can do about it. There is ongoing research into gene therapies, okay, but they all have, well, one problem is that the target is the brain, and you have to get whatever you want into the brain. And the human body has a very, very sophisticated barrier to the brain called the blood-brain barrier. And basically, the main way to get things into the brain is either to inject them directly into the brain or into your spine. Otherwise, in order to protect your brain and your central nervous system, your body blocks everything. So it's very hard to get things in there. And then, even if you do introduce UEB3A in there, or you somehow if you were to convince somehow the brain cells to produce UEB3A, it's not clear that it would change much of anything, because your intellectual development and your body's development has been you know, it starts in fact, for instance, you're learning to recognize the basic building block sounds of your mother's language when you're already in your mother's womb. So if you've missed that stage of development inside your mother's womb, you may never be able to figure out what a T or an F is, or what the different vowels are, or even be able to figure out that there are vowels in syllables. It just may never come to you because in the womb you didn't have it. So you would have to figure out how to. It's not clear at all that even if you start injecting this stuff into somebody's brain when they're 2 or 3 years old, whether it will make that much difference. So perhaps some of the gene therapies will give some incremental difference in outcomes, but that remains to be seen. But there's really no chance, I think, that we'll be able to cure Angelman, even though we know exactly what the problem is. There's another kind of disease where we know exactly what the gene problem is. It's called Fragile X syndrome. Again, it's only one gene, and again, despite an awful lot of work on gene therapies, we still don't have an answer. So you can know an awful lot about genes and how to treat them, but not be able to do anything for humans. Going on, I'll talk about cancer treatments. So something very sexy nowadays is the idea that that you can analyze the genes of a cancer growing within somebody, and maybe that person's genes as well, and based on the genetics of the cancer cells, design a specific treatment for those cancer cells that is more likely to kill the cancer and heal the individual. This is called precision cancer therapy, and there are several problems with it. One is that only a few % of people with cancer might benefit. Another one is that actually cancer cells are constantly mutating within the body, so that's part of the cancer syndrome, is that their genes constantly change. So even if your therapy works on one particular cancer within the body at one time, it may not work later or on the whole body. Okay. All the cancer cells spread out through the body. Another problem is that when you do apply this precision cancer therapy, often the result might be at best a few extra weeks or a few extra months of life, and those extra weeks and months may be filled with the person may still be sick and struggling. And another problem is that these precision therapies are actually combinations of other cancer drugs, and they're cocktails, as it's called. So two or three cancer drugs, and each of these individual cancer drugs may cost up to $500,000 nowadays. So you're just multiplying the cost of the therapy, and you're getting perhaps weeks or months, and there's no looking at people who have been treated with precision cancer therapy and people who have not. There's no clear evidence of an overall improvement in the outcome. So there's a lot of hype about it, but there's in general, and I'm sure that there are some cases, like I can think of an uncle who got some sort of experimental treatment. I don't know what it was, and his cancer went into remission, and is still in remission some 20 years later. So there are special cases, but in general, what you get from these, and I'm not sure that he got this precision treatment anyway, but in general, what you get is at best weeks or months at extreme cost, and only for a small percentage of your population. So overall, it's not a revolution in cancer. We're not anywhere near to a cure for cancer, as it's called. So overall, what I'm saying is that for all the progress in genetics, it's not really a revolution in the quality of life for human beings. So the two sciences that I think have been in major flux over the last 50 years are genetics. And the problem with genetics is specifically that we and everything that has genes is tuned. Okay, so you make a particular change, and it's very hard to know what a particular change's result will be, because it will have many different results, and so you're messing with a system that's far more complex than you can comprehend, no matter how much you analyze the system. And so, for instance, that's the thing with Angelman syndrome. There are so many consequences for that single one gene, and then you try to do something else to correct that, and that something else is not a simple reversal of. You would have had to reverse that particular gene problem from conception, and you're just not going to do it. It's the same problem with plants, and same problem with all the genetics things. You have a better understanding, but because you have a tuned system, it doesn't get you anywhere in terms of actually getting results, or not very far. Okay, and then with computing is the other discipline that's has gone through a revolution. Computing didn't exist in 1945, and by now it's slowing down. And also physics seems slower. So I want to talk a little bit about the roots of this slowdown. And I'm not talking. And when I concentrated on these, you could talk about all the other disciplines of all the hard sciences and all the engineering fields of engineering, and you could also look into the social sciences if you wanted, but these are the prominent ones. You can think of all the others and think, oh well, these haven't been going through the revolutions. Chemistry, for instance, engineering. So if only a few seem to have gone through revolutions, and they aren't really that revolutionary compared to what we were doing 100, 200, 300 years ago. Where are we? What is our actual progress? Is it accelerating or is it decelerating? It sounds like it's decelerating. Now, it could be that the reason for deceleration could be that we've already worked out the basics of most disciplines. So most fields of engineering, of the sciences, and so on. We've already learned the fundamentals and the foundations, and now, since we have the foundations, it's just going to be adding on. in perfecting things, and it could be that that's just the lay of the land, and this does happen. Fields do fields do have fundamentals, and then you can work out the fundamentals and then find that the rest is adding on. Okay, it does happen, and it has happened over and over again in many different fields. Okay, but I'm not sure that that's the case. That might not be the reason why things are slowing down, because there are also internal reasons internal to the human race. Okay. It could be that there are other revolutions waiting for us that could be just as transformative as the things over the last few hundred years, and we just aren't achieving them. Okay, I'm not sure of that. Okay, but it could be. At any rate, I think there are internal reasons why we aren't making progress as quickly either, and I think one of the one that I want to highlight is that everything in science is by now controlled by number crunchers, by what I call spreadsheets. You may know what a spreadsheet is. Around 1980, when the personal computer was developed, one of the principal things that people loved to use personal computers for was keeping track of large amounts of numbers in what was called a spreadsheet. And you would type in a number, suppose something that you spent today, and the spreadsheet would automatically do the tally for you of how much you spent in the last month. And maybe if you have it set up to do your taxes, it will give you, every time you put in another number, it will tell you how your taxes for the year will change. Okay, or whatever else you like. Okay, in other words, your personal computer could keep track of millions of numbers at once and keep you updated all the time about the status of your business, of your school, of whatever you were trying to manage, and therefore that gave people the opportunity to keep track of millions of numbers almost effortlessly, and to make decisions based on what those numbers told them. And in particular, nowadays, physics is based on three numbers in all of the sciences. One is, if you want to know about the quality of a scientist, or of a university, or of a particular group of scientists, then one number you look at is the number of published papers, that scientific articles that scientist published this year, or during his lifetime, or during the last 5 years. Then you also look at how many of those articles were in very high profile journals. There are certain journals that are extremely prestigious. There are other journals that are prestigious but more workaday, and then there are other ones that are perhaps acceptable but not really prestigious at all. And then there are other ones that are just junk journals. And so and the ones that are really paid attention to are the high prestige journals. If you can get published once, or preferably once every couple of years in a high prestige journal, you probably have a career in some high profile university ready for you. A third one that people pay attention to is how many other scientists cite your articles. So you publish an article. Whenever you publish an article, if it refers to or uses a concept from some other scientist's article, or some statistic from some other scientist's article, you're supposed to cite it. In other words, to actually call out, I'm using information from that other article. That's a citation. And at the end of your article, you'll have a list of citations of all the other articles that you're depending on, and so people can keep track of how many articles, how many people rely on your article that you just published. Or that, suppose I publish one now, then they'll look and see, okay, in the next year, how many people like my article so well that they choose to cite my article in one of their articles. And so you keep track of these citations. So a scientist who publishes many papers who gets them into high prestige journals, and who is cited by tens or hundreds or thousands of other scientists, that's a scientist who does well. Okay, and he's a high quality scientist. And same thing with a department of a university, a research group, or a whole university, or a country. Okay, so this is how we evaluate quality now, physics quality. It's based on these numbers, and there's a fourth number that goes with that. If you get those other three numbers right, then you'll be able to attract funding. In other words, a scientist will be able to go, or a group of scientists will be able to go and propose to some government organization, most likely, to give them money to spend on research. And so you can attract $100,000, $1 million, $10 million for a research project. And the more money you attract, the better scientist you are, and the more likely you'll be to get a good job, and also to be able to get yet more grants, get more money. So overall, this is how decisions are made about who to hire, about which universities are doing well, about whether a department is doing well, and so what scientists, universities, departments, and countries are aiming for is getting these numbers as high as possible. And so no longer do we have a situation where, in any sense, truth and real discovery are the overriding goals. Okay, this is not the goal of physics research or of scientific research anymore. It is in name, but it's not in practice. In practice, it's those numbers. And neither is teaching or formation a goal. Nowadays, instead it's more or less these numbers, and it's a kind of a popularity game. Popularity with other scientists, see how many scientists like you well enough that they cite you, and it's about fundraising. So what scientists now, if you're a successful scientist, you have to be a businessman. Okay, successful scientists right now are about attracting contracts, grants, and getting publicity. They're not scholars anymore. If you want to be a scholar, somebody who really cares about getting things right and is willing to take as much time as is required for it, then you're more or less where you were over most of the history of the human race. A scholar is somebody who wanders the world with a book in hand and is happy to have a pillow to put his head on. Okay, that's a scholar, and I think we're returning to that world. Okay, so in this world, it's based on numbers, these metrics. Okay, power belongs to the administrators and not to the faculty. It used to be that a university was run, and its fundamental decisions were made by its faculty, by its professors, and no longer. Okay, and we have a kind of power politics going on, where ideology, wokeness, DEI, diversity, equity, and inclusion make the decisions. And we have overall poor education and thinking and self-expression than 50 or 100 years ago. So in the US, many people graduate from high school without being able to read and write, and not being able to do basic arithmetic. And then if you are able to read and write at all and do basic arithmetic, you're in the upper echelon. We just aren't at the level that we were 25 years ago, and 25 years ago is worse than 50 years ago. And so I think when you have poor education at that level, it feeds into the level of research. And because people are playing a popularity game all the time, scientists only do safe research, and so they get, as a result, incremental or no improvement. And they research things where they're sure that they won't make waves. Okay, and they overplay every one of their results for significance and for publicity. So an example of overplaying it is these studies where you change a gene in some crop and you claim that it's drought resistant. Okay, and along the same lines, there are subjects that become popular that supposedly are groundbreaking new subjects in like drought resistance, gene therapy for plants, or in an example in physics that I'm very familiar with is something called topological physics, and it becomes it's played up as being a groundbreaking new development, and funding agencies become willing to give money based on, or a recent one is AI. So nowadays every scientist has to include AI in their research plan just to have a chance of getting funding. And so there are these fads based on funding sources, where the funding source says you have to have AI, you have to have topology, you have to have, I don't know, gene therapy. And so following the fads, following the funding source. Okay, so all of these are reasons why overall the quality of the research is not where it was. It's because we're not after real truth or real discovery, we're after some numbers and after popularity games and stuff. If you want to see somebody who's quite popular on the internet and has some similar criticisms of physics, though she's not entirely, I don't entirely agree with her, it's Sabine Hassenfelder. She's a physicist herself, and she is really strongly critical of physics in particular. Now I think there are some underlying reasons for all of these problems with the research atmosphere, and so we can go on and look more profoundly at the mechanisms of societal, that I think the underlying things have to do in a decay of our society, and I'll talk about this in other episodes coming up pretty shortly. Okay, so I've discussed in some detail where the sciences and engineering stand. We don't seem to be accelerating, and if anything, decelerating. And I have also said a word or two about why that might be happening. And now I just want to say that there's a even deeper problem other than evidence with this argument that humanity is accelerating towards something. The thinking is really deeply flawed. Their analysis, these transhumanists who talk about a singularity, their analysis of humanity's progress is focused on science and technology, and they don't really pay enough or much attention at all to other human affairs, the rise and fall of empires, the different cultures and the different cultural expressions, whatever goes on in the humanities, the different works of art, and the religions, and especially the religions. They don't pay attention to the human soul or spiritual matters. So I think this sort of focus on scientific and technological progress, and as if that summed up or were representative of the human race's progress, it really shows an extremely poor education. These people are not fully educated. They engage in something that I would call scientism, where everything, science reigns queen over everything, and everything else is insignificant. And the way that we evaluate human progress and anything that's worthwhile is according to scientific standards. So that's just it's beyond poor education. It shows no roots in humanity's true intellectual development. Another issue, and so I mean I could go on, but it would just be, I would just continue on in this same scathing direction, and I could elaborate on that as much as I wished if I wanted to take the time, and so could you. You could think of every worthwhile thing that anybody has said or done, every feat of government, or cooking, or or culture or or anything, or languages, development of languages. What would these people make of the disappearance of huge numbers of languages if they were to pay attention to that? The disappearance of cultures, of indigenous cultures. Would they think this is a good thing? But yet another problem, and I think that this is even worse, even more telling about these people, is that most of the human race actually believes that the critical moment, the turning point in human history, has already passed. So for Jews, they would say that Moses and his encounters with God, and God's bringing the Jews out of Egypt and giving them what they call the law, a rule of life, a rule for the heart, was a turning point, was the important turning point in human history so far. Many Jews also look for the coming of a Messiah, someone to bring in a world of justice and peace. So that would be a second turning point that they look for in the future. But it certainly has nothing to do with the transhuman singularity that we're talking about until now. Then Christians believe that God became man, and in Jesus Christ around 2,000 years ago. Moses, I guess, would have been closer to 3,500 years ago or something like that. Jesus was certainly 2,000 years ago. You can tell by today's date how many years ago it was, and give or take a few years. And he was born, and then God became man, and then you have this peculiar man-human combination walking the earth and transforming humanity, and then his death and his resurrection, and that he continues to animate humanity today. That would be the turning point in history so far. And Christians, I am one of them. We also look for another turning point, just as the Jews do, when heaven and earth will be remade, and Jesus will return in power this time. Then we go to the Muslims, and undoubtedly the Muslims believe that, and I think we can put roughly a date on it, that the Muslims would say that when an angel of God revealed the Quran to Muhammad, that would be the turning point of history. I'm not an expert on Islam, but I'm pretty sure that they would say that that's a turning point in history. I'm not sure whether they are looking for a Messiah, but I don't think so. Perhaps they're looking for Muhammad to return. I don't know about that, but certainly their turning point in history is more than 1,000 years ago. Then for Buddhists, I know even less about Buddhism, but I presume that when Gautama Siddhartha, this Indian prince, became the Buddha and achieved enlightenment, that would be a key moment in their history, in their version of history. I'm not sure whether they're looking for something after that, but between these we have the Jews, the Christians, the Muslims, and the Buddhists, all put the turning point of history somewhere in the past. Okay, and many of us do look for another turning point, but it's certainly not the turning point of the transhumanists. So it's okay for the transhumanists to have another opinion about turning points of histories, but the main question in my mind, the main objection that I have here is, why do they just disregard out of hand the opinion of the bulk of humanity? Why do they just ignore? They just show complete contempt for most of humanity and most of humanity's opinions about what the turning point of history is. So I think that also betrays a complete lack of education, and in fact I think a hatred on their part. So I think that regardless of the absence of evidence for any acceleration towards an intellectual singularity or a transhuman revolution, these people just have no intellectual foundation. Then, in fact, transhumanism at its core is not a scientific or a rational assertion. It's a new religion. Okay, it's clothed in technical language, but it's a religion. They reject the vocabulary of other religions, and they completely reject other religions. But they claim meaning and a transcendence, and they prophesy a coming of something. The transhuman, it's just they're in the same position as, say, the Jewish prophets were before the coming of Jesus, or as perhaps people preceding Moses were in expecting something like the Exodus of freedom from Egypt, or if somebody before Muhammad were to prophesy the coming of Muhammad and the Quran. That's the same position that these transhumanists are in. It's the same as there have been many sects recently that have been predicting the second coming, the apocalypse. They keep setting dates for it, and so far those dates have not actually come out true. These transhumanists are doing the same thing as many religious, and in fact they are a religion. And they also have ambitions to enforce or offer this on the whole human race. So if they had their way, they would try to make the whole human race engage in this turning point, however they think it's supposed to go. Okay. So it's not only a religion, but it's a power grab. These transhumanists are either themselves or people who promote them or are sympathetic to them are often many of those people are actually see a potential for obtaining power by this means. So you have a very rich person, for instance, who thinks that he might get to immortalize himself if the transhuman agenda succeeds, or at the very least he might be able to use the transhuman agenda to obtain a degree of control over the human race via AI, surveillance, digitalization, and so on, and by getting governments behind this agenda. So whether or not the people in power believe in this new transhuman religion, in this new singularity, it is an opportunity to obtain and exert power. Of course, in some sense, the transhuman agenda and this effort to obtain a singularity or a revolution, a reorganization, is not new. Okay, we've been for centuries pursuing an agenda of human progress, and of adopting more and more best practices and fighting over what the best practices are. From literacy to democracy to capitalism to socialism, all in the name, or communism, in the name of obtaining some kind of progress for the human race. And this has been used to justify a power structure that in some ways diverged at times. That you had, for instance, the communists versus the capitalists, but in other ways held many things in common and cooperated. So this is in a way just a continuation of the whole insistence on practices that will achieve a certain supposed good for the human race. So in some sense, I don't think that there's anything particularly new, except for that the religious nature of this is becoming more explicit. And the whole thing is, people were already willing to do unspeakable things in the name of progress for centuries now, and they continue to be willing to do those things. in summary of for the last two episodes, there's simply no sign that the human race is accelerating towards anything. If anything, we're decelerating. And there's no sign that we are of our own decision, all of us acting together in tight coordination and in one way cooperating or competing, that we're all going to organically adopt a new lifestyle or a new reorganization in order to match the conditions of the coming era without doublings and with a little less energy. What might still happen, and what I'll discuss in the next episode, is the possibility that there will be top-down control exerted, that some people in charge, perhaps publicly or perhaps hiddenly, will force the whole human race into a particular way of living that's better adapted to 30,000 calories per person per day and constraints on our resources. And I'll discuss whether that seems to be happening or not, whether it's going to happen in the next episode. After that, there will be an episode about computing and AI, and then we'll go on to some episodes about other ways that the human race may be forced to reorganize to match our new conditions in the following episodes. And then we'll finally have a summary of where the human race stands in this transition and what this transition is going to be like. We already have established that it's not going to be something where we, in some sort of fairly conscious way, are going to reorganize ourselves, except for perhaps by top-down. We'll cover that next time. So with that, I wish you a great week, and do keep coming back. And if you know anybody who would be interested in this content, please invite them to join in and watch. Do keep coming back. Yeah. Okay.